Hi everybody, it's Professor Mitchell. We're continuing with Chapter 3 on exponential and logarithmic functions. And today we're going to talk about Section 3.4, which is exponential and logarithmic equations. So in this section, we will use like bases to solve exponential equations. We'll use logarithms to solve exponential equations. And then we'll use the definition of a logarithm to solve logarithmic equations. We'll also use the one-to-one property of logarithms to solve logarithmic equations. And finally, we'll solve applied problems involving exponential and logarithmic equations. All right, so first using the like bases property, if you are able to write your exponential equation in this form, b to the m equals b to the n, then that must mean that m equals n. And that fact is a little deeper than it looks. That actually depends on the fact that y equals b to the x is a one-to-one function. All right, so to use this property, you first rewrite your equation in the form b to the m equals b to the n, and then set m equal to n, and finally solve the equation m equals n will probably be linear. Could be quadratic, but it'll be some kind of equation that you already know how to solve. All right, so two examples here. First, we have 5 to the power 3x minus 6 equals 125. And then we have 8 to the power x plus 2 equals 4 to the power x plus 3. Now, I decided that some of the examples in this section are complicated enough that I actually want to do them on my tablet instead of just presenting what's already written on the screen. I think you might get a little more out of that. But these ones are simple enough that I think we can just look at what's already on here. Okay, so for 5 to the power 3x minus 6 equals 125, we rewrite 125 as 5 to the power 3. So now our equation is in the form b to the m equals b to the n. Okay, the two bases are the same. So remember, whenever that happens, it means that your two exponents are equal. So in this case, 3x minus 6 equals 3. If we add 6 to both sides, we get 3x equals 9, and then divide both sides by 3 to get x equals 3. So the solution of this equation is 3. Now, the second one is just a little more complicated. So what happens in this one is I may not know off the top of my head how to write 8 as a power of 4. But what you can do is write both 8 and 4 as powers of 2, right? So you rewrite 8 as 2 to the power 3. You rewrite 4 as 2 to the power 2. And then use properties of exponents. Remember that the property that says a to the m to the power n equals a to the power m times n. So that's what I'm using here. So multiplying 3 times x plus 2, and I do the same thing over here. So now our equation is in the form b to the m equals b to the n. So I can set these exponents equal to each other. This is a linear equation. So of course, we're going to distribute the 3 and then distribute the 2. And if I subtract 2x from both sides, I get x plus 6 equals negative 6. Subtracting 6 from both sides, I get x equals negative 12. So the solution of this equation is negative 12. Now, sometimes it's not possible to write the two sides of your exponential equation with the same base. And in that case, you can use logarithms. So what you do to use logarithms to solve exponential equations is first isolate the exponential expression. And then, now I don't think the rule is quite as strict as what it says here. They recommend that you take common logarithm on both sides if the equation, if the exponential expressions are base 10, and use natural logarithm for bases other than 10. All right. I mean, I guess that's fine. You really can use either common logarithms or natural logarithms, but you do want to use one or the other of those because remember, those are the ones that are on your calculator. All right, and then simplify using one of the following properties. Remember my favorite logarithmic property, the power rule, says natural log of b to the x equals x times natural log b. You also have the inverse property, actually inverse properties, which say that natural log of e to the x equals x, or log of 10 to the x equals x. And once you have applied all those steps, you should get an equation that you already know how to solve, linear, quadratic, whatever. All right, so this is a good example to start with. I have no idea how to write 134 as a power of 5. So what we're going to do instead is start with 5 to the x equals 134. We will take natural log of both sides. I could have used common log. And then, let me get my pen here. I'm going to use my power rule, which says that I can take this x and go put it out. So that gives me x natural log 5 equals natural log 134. Now remember, natural log 5 is a perfectly good real number, which means you can divide both sides of your equation by natural log 5. And when you do that, you get x equals natural log 134 over natural log 5, which to 2 decimal places is approximately 3.04. Now notice, you remember in the last section we talked about the change of base formula. So the exponent that satisfies this equation would actually be log base 5 of 134. So what you get here is exactly what the change of base formula gives me for log base 5 of 134. Okay, just wanted to point that out. All right, next example. 10 to the x equals 8,000. Again, I have no idea how to write 8,000 as a power of 10, so I'm not going to use the like basis property. Now, this one has a base of 10. So I know they're going to use common log. That will give me a nicer answer, I will admit. Okay, so we start with 10 to the x equals 8,000. We take common log on both sides. Remember the inverse property that says log of 10 to the x equals x. So the exact value of this, the exact solution of this equation is log 8,000. And to 2 decimal places, log 8,000 is approximately 3.90. All right. Now, this one gets kind of ugly. All right. So I do want to do this one on the tablet. Let me just wake up my tablet here. I've got it all ready. So I actually had some technical difficulties with my tablet yesterday, so I was kind of relieved I got it working. Here we go. So there's that problem. Okay, let me switch to a thinner pen here. All right. So we have 3 to the power 2x minus 1 equals 7 to the power x plus 1. So the first thing I'm going to do is I'm going to take natural log of both sides. I could use common log. You know, I want to emphasize to you that it really doesn't matter. So we have natural log 3 to the power 2x minus 1 equals natural log 7 to the power x plus 1. And now I'm going to use my favorite property, the power rule for exponents, which says that I take these exponents and go. All right, so then what I have is, now I have to be kind of careful starting right about here. I have 2x minus 1, and I need to put that in parentheses because the whole entire thing is being multiplied by natural log 3. Same thing with x plus 1. X plus 1 times natural log 7. Now, believe it or not, that is a linear equation because natural log 3 and natural log 7 are both real numbers. Ugly, but I want you to try to understand that the steps for solving this equation are exactly the same as if it was 5 times 2x minus 1 equals 7 times x plus 1. Okay. Sometimes I say to classes, think of a simpler, happier time, all right? And then it makes the problem seem not so terrible. So if it was that nice, pretty blue equation, what I would do first is distribute the 5, distribute the 7. So that's exactly what I'm going to do with natural log 3 and natural log 7. All right, so what that's going to give me is the following: 2x times natural log 3. And I think I would like to write that as 2 natural log 3x minus natural log 3 equals natural log 7 times x, which I'm going to write like this, plus natural log 7. Okay, I admit it's ugly. All right, but it is a linear equation, so what do we always do with linear equations? We get all the x's on one side and get all the numbers on the other side. So let's start with getting the x's on, say, the left side. So I'm going to take natural log 7 times x, natural log 7 times x, and that is going to give me, well, it's going to give me 2 natural log 3 times x minus natural log 7 times x. If you don't mind, what I would like to do is, believe it or not, these are like terms. So I'm going to combine the like terms, and what that's going to look like is 2 natural log 3 minus natural log 7 times x. Okay? And then we have minus natural log 3 equals natural log 7. So I got the x's on one side. Now I'm going to get the numbers on the other side. I'm going to put the numbers on the right side. So I'm going to add natural log 3 to both sides. All right, so I think what I need to do now is go to the next screen, and hopefully I will remember. I may have to switch back and forth to make sure that I'm copying this correctly. So 2ln3 minus ln7, 2ln3 minus ln7 x equals, let me go back and peek, natural log 7 plus natural log 3. All right, we're almost done. So what we have at this point is a number times x equals a number. So we just have to get rid of the number that's being multiplied by x. We do that by dividing it on both sides. So that is 2 natural log 3 minus natural log 7. 2 natural log 3 minus natural log 7. Goodbye, goodbye. All right. Believe it or not, this is the end. So the exact solution to this equation is x equals natural log 7 plus natural log 3 over 2 natural log 3 minus natural log 7. All right, so let's switch back to the PowerPoint. Oops. And then, because I believe they're going to ask me first for an exact solution, which we just found, and then for an approximate solution, I am going to pull up the calculator to help with the approximate solution. This might be the first time I am ever using both my tablet and the calculator. So I'm kind of juggling here. Whoops. Okay. So this is what I just showed you. That looks almost exactly like the answer we got. But I want to make sure that you're able to get this approximate solution 12.11. So what I'm going to do now is plug in the calculator. And I just want to make sure that you're able to enter this expression correctly. So now let me share my calculator. Okay. So I want first that I put natural log 7 plus natural log 3 in parentheses. Natural log 7, and then close that one off, plus natural log 3, close off the whole thing, divide by 2, natural log 3, close that one off, minus natural log 7, close off the whole thing. 12.11439, blah, 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 which to 2 decimal places is, in fact, 12.11. Okay? All right, moving on to the next example. Okay. Using, what are we using? The definition of a logarithm to solve logarithmic equations. So your logarithmic equations come in 2 flavors. There are the ones that only have a logarithm on one side of the equation, and then there are the ones that have logarithms on both sides. If your equation has a logarithm only on one side, you use this property. So first express the equation in the form log base b of m equals c. And then remember at the very, not at the very beginning of this chapter, but in section 3.2, we talked about switching back and forth between logarithmic and exponential form. That was where we played the logarithm game, remember? So if log base b of m equals c, the base is b, and what is a logarithm? A logarithm is an exponent, and this logarithm is c. So the exponent is c. In this form, you should be able to solve it. It'll be linear, quadratic, whatever. Now, this is very important. Step 4. This is one of those situations, and you may have only seen this about one time before, where you have to check proposed solutions in the original equation. You can do steps 1 through 3 absolutely perfectly, and through no fault of your own, end up with solutions that are not actual solutions. We call them extraneous solutions. I like to call them posers, stowaways, something like that. So include in the solution set only values for which m is greater than 0. Remember, the domain of a logarithmic function is only the values that make whatever is inside the logarithm greater than 0. So that's the only thing that can go wrong with these. You can end up with proposed solutions that are not in the domain of your logarithmic function. Okay, so for our first example, and I don't need to do this one on the tablet, we're going to solve the equation log base 2 of x minus 4 equals 3. So the base is 2, and what is a logarithm? A logarithm is an exponent, and this logarithm is 3. So when I write this equation in exponential form, the exponent is 3. See that? So in exponential form, this is 2 to the 3rd equals x minus 4. That is a little baby linear equation. 2 to the 3rd equals 8. 8 equals x minus 4. I just add 4 to both sides. That gives me x equals 12. So now we want to make sure that this is not a poser solution, that this is an actual solution. So you put it in the original equation, and it gives you log base 2 of 12 minus 4 equals 3. So we ask ourselves, is that true? Well, 12 minus 4 is 8, and log base 2 of 8 is in fact 3. right? Log base 2 of 8 is the exponent to which you have to raise 2 to get 8. So that exponent is 3. This solution checks. This is an actual solution. All right, next we have 4 natural log 3x equals 8. This is another one that's relatively simple. I'll just show you this one on here. So first thing I'm going to do is divide both sides by 4. That gives me natural log 3x equals 2. Now, what you might find helpful, except shoot. Okay, well, let's do this. Where'd it go? Oh, okay. Remember, oh shoot, hold on. There we go. Remember that natural log is log base e. I don't know how to do subscript on this Zoom typing thing. So log base e, and that might help you figure out how to write this logarithm in exponential form. Bear with me for 1 second while I find my mouse. There we go. Okay, so the base is e. What is a logarithm? A logarithm is an exponent. This logarithm is 2. So the exponent is 2. So in exponential form, this equation is e squared equals 3x. Divide both sides by 3, you get x equals e squared over 3. That does need to be checked. So if you check it in the original equation, the 3's cancel. I get 4 times natural log e squared equals 8. By the inverse property of logarithms, natural log of e squared is just 2. So 4 times 2 equals 8. Of course, that's true. So this solution checks. Interestingly, they did not give an approximation for that solution. Often they do that when it comes out to something like that. So maybe just pick up your calculator and verify that to 2 decimal places, e squared divided by 3 is about 2.46. Okay. Just in case they ask you for the approximate solution. All right, next we have this one. I'm going to do this one on the tablet. We have log x plus log x minus 3 equals 1. So let me, oops, I have to unplug the calculator, plug in the tablet. And now we will go over to the tablet. And there it is. Log x plus log of x minus 3 equals 1. Okay, so notice we have 2 logarithms on the same side of the equation. What you do in this case is use your properties of logarithms, either the product rule or the quotient rule, to combine those into a single logarithm. So what I mean by that is you take log x plus log of x minus 3 and you rewrite it as log of x times x minus 3. Remember the product rule for logarithms? Okay. And now it looks kind of like what we've been doing. Remember that log with no base means base 10. It might help you to scribble a 10 in there when you go to write this in exponential form. So the base is 10. And what is a logarithm? A logarithm is an exponent, and this logarithm equals 1. So the exponent is 1. That is equal to x times x minus 3. So this is a quadratic equation. 10 to the first power is 10. And if I distribute this x, I get x squared minus 3x. So now I am going to put this quadratic equation in standard form by putting everybody on one side. And that's going to give me x squared minus 3x minus 10 equals 0. I'm going to solve that by factoring. Okay. So in order to factor that, I have to come up with two numbers that add up to -3 and multiply to -10. So those two numbers would be -5 and +2, wouldn't they? All right. So of course, if x minus 5 times x plus 2 is 0, that must mean that either x minus 5 is 0 or x plus 2 is 0. If x minus 5 is 0, that means x is 5. And if x plus 2 is 0, that means x is -2. Now, don't misunderstand. I'm circling these answers, but at this point, these are only proposed solutions. So I'm going to go back to the PowerPoint to show you the check. All right. So there is what we just did. Wow, it looks almost identical to what I wrote on my tablet, except, of course, theirs is a lot neater. All right, but here's the check. So first check the 5. When you put that into the original equation, you get log 5 plus log of 5 minus 3 equals 1. In other words, log 2 equals 1 by the product rule. Log 5 plus log 2 is the same thing as log of 5 times 2. 5 times 2 is 10, and the log of 10 equals 1. Because this is asking what power do you have to raise 10 to get 10? The answer is 1. However, when you go to put the -2 in the original equation, the first thing I see is log of -2. And that doesn't work. -2 is not in the domain of any log function, right? So we have to throw out that proposed solution. That is a poser. The only actual solution of this equation is 5. Okay, now it also happens that you have logarithms on both sides of your equation. So what you do in that case is you write the equation in the form log base b of m equals log base b of n, and then use the fact that logarithm is a one-to-one function, similar to what we did at the beginning of this section with b to the m equals b to the n. Since logarithm is a one-to-one function, that means that if log base b of m equals log base b of n, that must mean that m equals n. Okay? And once again, this equation will be linear, quadratic, something that you know how to solve. And finally, since it is a logarithmic equation, proposed solutions must be checked because there might be posers. Okay, so the first example, I'm going to do this one on the tablet. It's a little ugly. Natural log x minus 3 equals natural log 7x minus 23 minus natural log x plus 1. So let's switch over to the tablet. And the first thing I'm going to do, since I have two logarithms on the right side of the equation, I'm going to use my quotient rule to rewrite that right-hand side as a single logarithm. So instead of natural log 7x minus 23 minus natural log x plus 1, it's just going to be natural log 7x minus x plus 1. That's the quotient rule, right? All right, and then this one-to-one property of logarithms says basically if log this equals log this. In other words, x minus 3 has to equal 7x minus 23 over x plus 1. Okay, so this is actually a rational equation. Fancy, fancy. So the way that we solve rational equations is we multiply both sides by the LCD, which in this case is just x plus 1. So I'm going to multiply both sides by x plus 1. Notice that this really needs to also be in parentheses. So that's going to give me x plus 1 times x minus 3 equals 7x minus 23. It looks like this equation is going to end up being quadratic. So to put it in standard form, I am going to FOIL these two. That's going to give me x squared minus 2x minus 3 equals 7x minus 23. And then to put it in standard form, I am going to subtract 7x on both sides. And I'm going to add 23 on both sides. So now I'm going to go to the next page to finish this off. Minus 9 plus 20. Okay. That gives me x squared minus 9x plus 20 equals 0. And again, I'm going to solve that by factoring. So I need two numbers that add and multiply to positive 20. Those would be negative 5 and negative 4. So if x minus 5 times x minus 4 equals 0, the only way that could happen is if either x minus 5 is 0 or x minus 4 is 0, which would mean x is 5 or x is 4. But those are only proposed solutions. So let's go back to PowerPoint. We'll look at the check. I think these two end up both checking. Well, let's see. All right, so there are the proposed solutions. And here is the check. So when I put in 5, what I end up with is natural log 2 equals natural log 12 minus natural log 6. And when you use the quotient property to put those together, you end up with natural log 2 equals natural log 2. So that looks fine. And when you put in 4, what you end up with is natural log 1 equals natural log 5 minus natural log 5. If you use the quotient property to put those together, you get natural log of 5 divided by 5. So natural log 1 equals natural log 1. These are both legitimate solutions. This equation has two solutions. All right, and that brings us to a couple of little applications. I decided to just present these off the PowerPoint, so hopefully that'll be okay. I'll take it nice and slow, and of course, since you're watching this on a video, you can pause it anytime you want. Okay, so the question is, how long to the nearest tenth of a year will it take $1,000 to grow to $3,600 at 8% annual interest, compounded quarterly? So we're going to use the compound interest formula that we saw, I think that was back in section 3.1, the one that looks like this. So I put in 1,000 for P, 3,600 for A, I put in 0.08 for R, and I put in 4 for N, because quarterly means 4 times a year. So I end up with this equation. 0.08 divided by 4 is 0.02. Of course, 1 plus 0.02 is 1.02. So this is an exponential equation. So what I need to do now is isolate the exponential expression, which means divide both sides by 1,000. 3,600 divided by 1,000 is 3.6. So we have 3.6 equals 1.02 to the power 4t. So this is the type of equation where you have to take a logarithm on both sides, and they would use natural log. And then I never miss an excuse to do this. Natural log of 1.02 to the power 4t. That 4t comes out front. So that gives us natural log of 3.6 equals 4t times natural log 1.02. To get t by itself, you would divide both sides by 4 natural log 1.02. That is a perfectly good real number. So the exact solution is natural log 3.6 divided by 4 times natural log 1.02. Let me just remind you that if you're doing this on the calculator, you would need to put this whole entire thing in parentheses. And to the nearest tenth of a year, that comes out to 16.2 years. It'll take 16.2 years for your $1,000 to turn into $3,600. And for the last example, I think we did an example like this with boys a section or two ago. Now we're going to do it for girls. The percentage of adult height attained by a girl who is X years old can be modeled by the function f of x equals 62 plus 35 times log x minus 4. So I believe that's slightly different from the one for boys, where x represents the girl's 15, and f of x represents the percentage of her adult height. The question is, at what age has a girl attained 97% of her adult height? So we're going to take our formula and we're going to substitute 97 for f of x. That gives us 97 equals 62 plus 35 log of x minus 4. We subtract 62 on both sides. That gives us 35 equals 35 log of x minus 4. We divide both sides by 35. That gives us 1 equals log of x minus 4. We write that equation in exponential form, which would be 10 to the first power equals x minus 4. Add 4 to both sides, you get x equals 14. So the age at which a girl has attained 97% of her adult height is 14 years old. And that's going to do it for section 3.4. We'll see you next time for the last section of chapter 3.